Welcome. The subject of this video is going to be using Arduino interrupts. I'm your host, Lewis Laughlin. Visit my website at www.bristolwatch.com and please subscribe to my YouTube channel. What does an interrupt do? Interrupts allow a microcontroller to perform its main task without constantly polling the input pins. That is, it doesn't sit here constantly checking the electrical status of an input pin. Most Arduino boards have two external interrupts, interrupt 0 on digital pin 2 and interrupt 1 on digital pin 3. The Arduino Mega has an additional 4 interrupts labeled 2 through 5. Here we're interested only in interrupt 0 and interrupt 1. There are 4 available functions for controlling interrupts with Arduino: DetachInterrupt, DetachInterrupt, interrupts, and NoInterrupts. Really, what does an interrupt do? What goes on in the mind of Arduino or another microcontroller when it receives an electrical signal that tells it, hey, this is an interrupt. Stop what you're doing and take care of my problem. The sequence runs something like this. Arduino finishes its present instructions. It immediately blocks all other interrupts. It saves the current address location on what is called a stack. A stack is a RAM location internal to the microcontroller that's a temporary permanent storage area. It jumps to what is called an interrupt service routine, often abbreviated as ISR. The ISR completes a program and then it executes a return. A return tells the microcontroller, yes, I'm finished with this program. Let's go back and undo what I did to get here. First, the Arduino pulls the original address location from the stack. It re-enables the other interrupts, and then it continues as before. So it's a sequence of basically finish up, block the other interrupts, save the address, go do something it was programmed to do, whatever it was supposed to do, issues a return, and then the process is reversed. Here is the diagram to my actual Arduino test circuit. I drew a simplified version of an Arduino Nano. And in this case, I have connected 2 switches. I had to debounce my switches that are connected to digital pin 2 for interrupt 0 and digital pin 3 for interrupt 1. When you're using a signal to interrupt on a digital pin, you need a clean signal without electrical noise. So that's what the purpose of this debounce circuit was. Using regular switches directly connected to Arduino is going to create false interrupts and foul up my program. On the output side, I've connected 2 LEDs, LED 1 on digital pin 9 and LED 2 on digital pin 10 through 470 ohm resistors to ground. This is our basic test circuit. The rest of it can be executed from here in software. In the case of these debounced switches, the signal level on digital pin 2 and 3 with the switches open is 0. When I press the associated switch, it will go from low to high. Let's look at our first very basic interrupt program. I've defined LED as being on pin 9, and I have a byte called volatile byte, which I name state equals low. This is something we need to keep in mind for using interrupts. Byte is the type of variable I'm using. Now, a lot of these sketches uses an integer. That's a waste because I'm not using a number greater than 255. Use a byte and you'll save a byte literally. A integer uses 2 bytes as where a byte uses a single byte. What is important is this statement volatile. It's a special kind of variable where it's stored in RAM. This is much more stable and much more accurate as opposed to a register. If we move down, our setup routine, I just set up my LED pin wherever I got the LED connected as an output. Now I'm going to use an interrupt specific command, DetachInterrupt 0 blink rising. What this means is I'm going with interrupt 0, that's on digital pin 2, Arduino knows that. A interrupt service routine is blink, that's my interrupt service routine, and the characteristic of the electrical system is rising. When it goes from low to high, the interrupt will run through its sequence of halt on the last instruction and shut down any more interrupts, go do my interrupt routine, and come back. That is the electrical condition that it's looking for on digital pin 2. When I press that switch and it goes from low to high or rising, it will jump to the interrupt service routine blink. Blink is down here at the bottom. All it does, remember we had this byte volatile style variable and it was set low. The little ISR routine blink is simply state equals not state. That is, if the state variable was a 1, now it's a 0. If it's a 0, it's a 1. Note something here, looks like a regular subroutine, except for this last curly brace is considered the return. This is the return from interrupt as far as Arduino knows. So I sit here, I load this program, the LED is off for the first run. I press the switch, it goes high to low. The ISR routine blink will be instituted. The output, if you look here in loop, digital write LED state, as where the LED was off, if state goes from 0 to high, well, it's going to leave here, go back to loop, and the LED will turn on. That is, all you're doing in this little program is every time you press that associated switch on digital pin 2, the LED comes on, press it again, and then it goes off. In the previous slide, we used the DetachInterrupt function, and at this point, this needs a much more in-depth explanation. DetachInterrupt has 3 variables. Interrupt, that's in this case interrupt 0 for digital pin 2 or interrupt 1 for digital pin 3. Function, that's your ISR interrupt service routine, and mode. Mode has 4 definitions that Arduino recognizes. Rising we already saw. If we go by the previous program and the schematic that I showed in earlier frames, when I press SW0, the voltage level on digital pin 2 goes from low to high and thus triggers an LED toggle. If it's on, it goes off. If it's off, it goes on. Whatever. The next one is falling. If I press the switch in and hold it, nothing happens because it went from low to high. But when I release the switch, it goes from high to low, then the LED will toggle. That's what falling means, is from low to high. Then we have a third one called change. If I press the switch, the LED will toggle. If I release the switch, it will toggle again. Change means either low to high or high to low. Again, change, any change on the electrical pin, be it high to low or low to high, will trigger the interrupt service routine. Then they have a fourth one called low. I tested it. It's erratic. Don't use it. I mean, I don't see the use of it. It sort of acts like falling, but it's really erratic. I don't see the purpose of it. Alright, let's look at this slide up here. This is a normal subroutine you will see in Arduino called toggle. If I send a pin number such as pin 9 or pin 10 to this subroutine, it will read the state of the pin and that not digital read pin number. If it's a high, it'll return a low. If it's a low, it does a high. So instead of state equals non-state, by using not digital read, I do the same thing. Then it immediately writes that inverted state back to the pin. Now in this case, I have defined two interrupt service routines. ISR0 is digital pin 2 and ISR1 is digital pin 1. Instead of writing this routine inside of both interrupt service routines, I merely call a separate function or subroutine from the interrupt service routine. This is perfectly fine. But remember, we still have the same rules. When I go into an interrupt service routine, until I do this last curly brace for a return, all of the other interrupts will be blocked. While this works fine in this routine, it won't in the next routine. Here I have changed my toggle function slightly. It does pretty much the same thing. It reads the state on a output pin, inverts it, writes it back. It delays for 1 second and then does the same thing again. Pin state equals pin state XOR 1 is the same thing as pin state equals not pin state, nonetheless, and writes it back. When I call it from my ISR service routines down here, it doesn't work, but it works fine when I call it from something in loop. Why is this? Here is your problem. The function delay requires the use of interrupts. You don't see this when you use delay 1000, but it's using interrupts internally. When I try to use delay or several other functions within the interrupt service routine, or try to call it in functions from the interrupt service routine, it doesn't work. It's because why? When I enter an interrupt service routine, what is one of the first things it does? Blocks all the other interrupts. So there has to be a way around this problem. The obvious way to get around this is to write your own millisecond delay routine. Fortunately, the function delay microseconds does not depend on interrupts and will work within an interrupt service routine or will work in those functions called by interrupt service routines. If you remember, 1000 microseconds is 1 millisecond. And so what do we do here is I just made my own little function, my delay. If I need to delay 1000 milliseconds, that's fine. And it just loops through and does X number of 1000 millisecond delays. If you look down here in this interrupt service routine, here when I press the switch tied into digital pin 3, it will, of course, toggle LED 2 and use my delay and wait around 5 seconds. Then it will toggle it back off. This flag equals 0 is something entirely different that will be explained back on the website. I don't want to get into it here. And note, until such time that I call this last curly brace, it will block any interrupts from interrupt 0 until such time that I am through with the service routine for interrupt 1. Alright, in this slide we have a small program running in loop. It just turns on an LED for 2 seconds, turns it off for 2 seconds, and repeats. During this time, if I have an interrupt, anytime during this on, say, interrupt 0, it will go ahead and toggle the LED, and this is assuming the toggle routine is there. And it looks like loop doesn't even know it, but what it actually does is stop loop wherever it was. It goes through its save the address and shut off the interrupts and that stuff. This interrupt service routine down here does its thing and returns back to that point where it interrupted loop, and it will go on. Now, the fact that you're using a interrupt-based routine like delay might throw the timing off. I'm not sure, but it probably does, so keep that in mind. Now we come to a function called DetachInterrupt 0. What this does when you do a detach interrupt down here in loop or wherever, or even back in the ISR routine, it blocks any interrupts from interrupt 0. If you're pressing the switch multiple times while this is going on, it's going to ignore you. But at the same time, if you press the switch on interrupt 1, it will remember it, but it won't act on it until you do an attach interrupt 0, and then it will execute the interrupt 1 routine. Let's go through that again. Detach interrupt, in this case, allows this LED to go on and off, and interrupt 0 and interrupt 1 cannot interfere with it. All right? But if you happen to have interrupt 3 and you try to use it during this time, it won't act upon it until I do an attach interrupt 0. Then it will service interrupt 1. As a final note here, when we use detach interrupt 0, it does not interfere with the interrupts that are used in the delay routine, so you don't have to resort to using my delay. So when you use detach interrupt, it blocks interrupt 0 and it seems to block interrupt 1, but it does not mess with all the other interrupts that's used by the other functions. Here we go with another example. Here is the use of NoInterrupts and the interrupts function. NoInterrupts does just what it says. The only problem is it also kills the interrupts used by the delay routine, so you will have to use your own delay routine like the one I wrote. None of the interrupts will work until you issue the command interrupts. You would want to use this if you've got some really particularly tricky timing that you do not want anything else messing with. So remember, if you use NoInterrupts, all the interrupts hardware types, including delay and some other functions, no longer work, and you will have to write your own delay routines. Hopefully now you've got an idea how to program interrupts, and we know how to get them to react with a switch. Now we're going to look at a direct application that I've had up on YouTube before. This is a zero crossing detector. What it does, it produces a pulse from low to high at 0, 180, and 360 in a sine wave. These pulses are a way to synchronize to the AC power line, so you could use a microcontroller to control various power circuits. This is what a zero crossing detector does every time. Again, at 0, 180, 360, you get a pulse. We apply this pulse, of course, to an interrupt. In the case, I usually use interrupt 0 on digital pin 2. Here is an example circuit. It's in more detail in other videos and on the website. I'm using the interrupt 0 on digital pin 2 to synchronize to those zero crossing pulses. I use this pot to generate a delay, and then after a delay, I send a firing pulse to this optocoupler that turns on this triac. and that way I can control the amount of power getting to the load. Here is the entire routine. If I didn't show the switch attached to it, but it's in the other schematic. If I have a switch which is normally reading high, I didn't debounce the switch, by the way. No, excuse me, I am using the debounce switch here. If I push the switch on, I'll call it SW, which is digital pin 0, what it does at that point down, it attaches the interrupt. This is down in loop, not in setup. Press the switch, I attach interrupt 0. I'm going to use the ISR routine AC on, and I'm going to use falling. If I don't press the switch, I'll have a detach interrupt and it does nothing. But with the interrupt attached, what it does, it's going to delay microseconds based on reading analog 0, the value of the pot, multiplying by 7 and adding 500. This is the delay microseconds routine, which is good for up to 16 milliseconds. The delay microseconds can be used up to about 16 milliseconds, which is fine, because I'm only using it for around 8.35. After that delay, I'm going to do a digital write to a pin designated as triac pulse. That's the electrical signal that's sent to that optocoupler, goes high. I'll delay 50 microseconds, then I'll go low. The minute that I go high, I trip on that optocoupler triac combination to turn on the AC power. And then I turn it off. That can sort of be illustrated here. Either though I'm using pulsating DC, it works the exact same way with the AC. Here's my 0 crossing pulse. I get an interrupt. I read the pot. I calculate a delay. Say I calculate a 2 millisecond delay. I cut on the half cycle at 45 degrees. The light is going to be pretty bright. Alright, the next time I get it, I adjust the pot for a 4 milliseconds delay, and here is my 0 crossing pulse on the interrupt. It goes to the interrupt service routine, delays 4 milliseconds, and puts out a triac trip pulse, and it's turned on until it goes to 0. If I delay 6 milliseconds, I'm waiting a fairly long time before I switch the triac on, and I'm not transferring much power. The light is dim. So very little delay between the interrupt and 0 crossing pulse. Lots of light. Delay 4 milliseconds, it's half on. Delay 6 milliseconds, it's not on much at all. And that's an introduction on how to use interrupts, and you'll see 2 small video clips following this showing this principle in action on an oscilloscope and how you can control pulsating DC and AC using interrupts and a 0 crossing pulse. Thanks for listening, and I hope this was helpful. Alright, what you're looking at again is my oscilloscope. On the top of the video you will see full wave pulsating DC. The bottom half of the video is where I'm using AC phase control with a silicon controlled rectifier or triac, if I'm using a diode bridge, to control the on time of each half cycle. If you look here, you have full power delivered to the load. There, as you can see, is no power delivered to the load. The secret is that you're going to detect the 0 crossing pulse, which in this case is here or wherever. Then you're going to delay a specific set a time delay before you trip on the triac or SCR based on a potentiometer that's connected to my Arduino Nano. Yep, this is being powered by an Arduino Nano. Both the zero crossing detector and the drive to the SCR is done through optical isolators in order to protect, once again, the 5-volt circuitry. You just cannot get around opto isolators for power and flexibility. Let's move on. This time we're looking at full wave AC, which is going to be your top trace. And now I'm just using the triac as a triac and not through a diode bridge. And if you notice each half cycle below, be it positive or negative, I can control the on time. And particularly right here, for instance, my light is very bright. Here it is very dim. This is what you call phase angle control, or phase control. And of course it's being done by an Arduino Nano. What good is something like this? Okay, say you first cut on a heater. Maybe you're doing an incubator for chicken eggs, argumentatively, and it gets really cold and you need to crank the power up into the heat source. Let's cut it on full power and get it up, and as you measure the temperature and as you approach the desired temperature that you want, you begin to electronically cut back on the amount of energy being delivered to the heater. And when it reaches the point that you want, you just put in enough energy to keep the device at a fixed temperature without overshooting and having it go down. This also saves a lot of energy.